Good morning, grade 9 students. I hope you're doing well. Today we will have our first e-learning lesson. It's going to be about thermal physics. We will be continuing from the point where we stopped 2 weeks ago. So basically, we are going to continue with specific heat capacity and specific latent heat. Before I start with thermal physics, I want to tell you about how things are going to go with this e-learning sessions. Basically, I'll be posting this video explaining the topics every time that I will discuss. And then I will be also uploading an assignment that you have to finish before the next session. Our sessions are going to be on Monday and Thursday. So today, Monday, I am posting this video, and I'm also posting the assignment. You have to log in to LMS on Digital Campus. You watch the video, and then you complete the assignment, and then you upload it back to Digital Campus, either by taking screenshots of your textbooks or by scanning the papers and uploading it. It's very easy. You have to make sure that you do that before the next session, which is on Thursday. And the same thing on Thursday, you have to make sure you do the assignment before Monday. Also, there will be a quiz on next Sunday about all of thermal physics. It's going to be a multiple choice quiz. I will tell you it's going to be on Monday at 9 a.m. and we will be discussing it further this Thursday. Now, what I'm going to be talking about is basically I will be revising quickly measurements of temperature and thermometers. It's something that we did before, but I will go over it again very quickly. Specific heat capacity, we started it, but I will make sure that it's complete, and then I'm going to talk about specific latent heat. So these are the three topics that I'm focusing on today. Let's go over thermometers again. The first type of thermometers that we talked about was the liquid in glass thermometers. We talked about its parts, its shape, and how does it work. The property that changes as temperature changes is the volume or the density of the mercury, and it doesn't have to be always mercury. We can use different liquids depending what we want from that thermometer. There are other properties that work with other thermometers like resistance or voltage, which is basically what works with thermocouples. The color is for the thermometer where the color changes, which is the liquid crystal thermometer that we talked about. Calibrating thermometers works with finding where the 0 should be and where the 100 should be. The 0 where you put the thermometer in a melting ice. So it's ice melting into water, whereas this one, it's a water boiling into steam where we are sure that the temperature is 100. And then as you can see here on this thermometer, after we get the 0 and the 100, we can put equal divisions between them, and this when we are sure that the scale is linear. Now, the other type of thermometers that we talked about were thermocouples, the hot junction, the cold junction, and how they are connected with the wires. As you can see, this is a copper wire here, and whereas this one is iron, the materials are going to be different here. As you can see, it's written galvanometer, or even if you put a voltmeter, you are completely fine. Basically, the quantity that changes here is resistance or voltage. So that's the only thing that you can say when it changes. We talked about the properties of it. When is it good? It's good for rapidly changing temperatures, high range, high temperatures, and it's also more precise because it gives more decimals with the reading more than the regular thermometer. What we talked about here also was specific capacity. We did this experiment in the lab, if you remember, guys. So we measured the specific capacity either for water or for aluminum. That's the experiment that we did. We knew that specific heat capacity equals MC delta T, which is the formula that you can see over here. And the definition of specific heat capacity is the amount of energy required to raise the temperature of a 1 kilogram substance by 1 degree Celsius. Here I have the units for you to make sure that you put everything in the right units. And here I also have the formulas that we will be using. So again, the energy that you need to raise the temperature of a certain material is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature, which is the difference between the high temperature and the low temperature, whether it's going up or going down. Now, those are the sources of inaccuracy in the lab that you did, and these are the solutions of how to make these inaccuracies not as much. So let's talk about this question first. I'm sure you will be able to solve it very easily. The question is, there is a beaker that contains 0.5 kilograms of water at a temperature of 3 degrees Celsius. So far, we can tell that this one is the mass, and this one is the initial temperature Ti. And here is the internal energy has increased by 21 kilojoules. This is Q. And they give us the specific heat capacity, which is C. Now, the question is to find what is the temperature of the water after the energy has been added. So the question is to find T final. Now, we cannot just find T final straight away because we can use this equation over here, which allows us to find delta T. When we find delta T, which is how much the energy, how much the temperature has increased, we have to add it to the initial temperature to find the new temperature. So we will use the equation, which is delta T. To find delta T, it's going to be equal to Q over MC, which is 21,000. Again, that's a trick if you don't put 1,000 because it's in kilojoules, over 0.5 times 4,200. When you do this calculation, it means you're dividing 21,000 by 2,100, and this will be 10 degrees Celsius. Now, if you rush and you choose this 10 degree, you're getting a wrong answer, especially if that's a multiple choice. The question is not to find the change in temperature. The question is to find the new temperature. So if the original was 3 and we have an increase of 10, the right answer is 13 degrees Celsius. Okay, so that's a tricky question of how to find the final temperature. The next new part that I'm talking about is the specific latent heat, and that is something new that I want you to focus on, which is the specific latent heat. Specific latent heat is, as a definition, is the amount of energy needed to change the state, not to just change the temperature, change the state of a 1 kilogram of a substance at a constant temperature. So I want you to, in the exam, if they ask you define, make sure to say the temperature doesn't change in the definition. So that's something very important, because when we are doing fusion, which is melting, so fusion, it's basically melting that we are talking about. Whenever this happens, or if boiling, temperature stays constant, either at 0 or at 100 degrees Celsius. Now, how much energy do I need? For example, if you look at the experiment, we had some crushed ice, and we are melting them into water. So this is a change in state. We are not changing the temperature of ice. We are basically changing the state of the ice from solid to liquid. Now, the energy I need to melt some parts of this ice into water is given by the equation Q equals ml. As you can see in this equation, there is no delta T because there is no change in temperature. So I will never use delta T in such a question. L is the specific latent heat, which is a property of every material. The same way we had a different specific heat capacity for every different material, we have a different specific latent heat for different materials. Now, ice has its own L that we can calculate. What is this L? It's the amount of energy to melt 1 kilogram of ice into water at a constant temperature. Now, the units of Q again is going to be joules. The unit of the mass is kilograms, and L will be joules per kilogram. So anytime I talk about the specific latent heat, the unit is going to be joules / kilograms. Basically, this experiment, as we did the same way we did it in the specific capacity in the lab, if you remember 3 weeks ago, you have to connect the heater into a power supply, and then in this heater, you can either find the power or you find the current and the voltage, and then you multiply them because power is equal I times V. So that's how you find the power, and then Q, we found it by the equation P times T. And then once you find P, you can find easily L using this equation again, Q equals ML that we talked about. Now, what M is it? It's the mass of the ice that has melted. So if at some point you start the experiment, you start recording the time, and there's already some water in the beaker, I don't have to use this water because that's the water that melted before I started measuring time. So what I do is that I find the mass before I start, or the moment I start and the moment I finish, and the difference between them is the mass that I actually melted during the time I was recording it. So make sure that you're finding M in this kind of experiment, it's equal to M2 minus M1. So that is a trick because again, the mass that you are using in this equation should be the mass that melted during the time that you were recording in the experiment, which is something very important. If you look at this question over here, we have a heater, like the one we're talking about, and the power is given for us directly 100 watts. So sometimes they might give you I and V, you have to multiply them, but here they give us the power straight away. And the time is 500 seconds. Again, sometimes they might give it in minutes, so make sure to change it. And they said the mass of the water boiled away is 20 grams. So here they are not melting ice into water, they are boiling water into steam, which is the same thing, because anytime there's a change in state, I use this equation Q equals ML. So guys, I want you to focus on this. If we are changing the temperature, we use Q equals MC delta T. But if we are changing the state, we use Q equals ML. In this case, they said boiled. Boiled, it means we're going from water into steam. And whenever we're going from water into steam, that's a change in state. So that's why, as you can see in this equation, we used Q equals ML. Now the question was to find the specific latent heat of vaporization, which is L. To find L, we need Q and M. Q, we don't have it in this question given straight away, but we can easily find it by multiplying power with time. So we get 50,000 joules, and then we divide it by the mass. And as you can see here, this mass was changed into kilograms by dividing it by 1,000. So that's a trick that some of you sometimes would do, and it happened in our last exam. So please make sure that you change it to kilograms, and that's the answer of L, which is 250,000 joules per kilogram. Now there are some precautions in the experiment of finding the specific latent heat that if you remember, we did not start the experiment until we saw there is a change in the temperature. And here we don't, in this experiment, we don't start recording the time until we see the water flowing down at a constant rate. That's when we see that melting has started. And we use crushed ice rather than big pieces because they have a larger surface area, so they can melt more easily, because each piece by itself is absorbing the heat. So there is better contact between the heater and the ice. So that is something really important to look at. I have one past paper question I want to solve with you. which is coming now. But first, let me talk about this graph. This graph shows which part to use, which equation to use in each part. If you look at the part from A to B, the temperature is increasing. So which equation do I use? It's Q equals mc delta T, because there is a change in temperature. Whereas from B to C, the temperature isn't changing. So in this, you use Q equals ml, because there's a change in state, and that is melting. Here again, we get the temperature is changing. Whenever temperature is changing, again, it's mc delta T. Here again, there is boiling because the temperature isn't changing, so it's ml. By the way, this is called F, fusion LF, and this is LV. There's a small letter under the F to differentiate between them. And this one here, again, it's mc delta T because the temperature is changing. So that's why you need to know which equation to use in which state. Anytime there is the same state like the one here, and the temperature is changing, that is mc delta T. Anytime there's a change in state like melting or freezing, we use a different equation. So it's quite important to look at these to know which part, which formula to use for each part of the graph. So it's important to know what is happening, and then you know which equation you can use. This question is about specific heat capacity that you need to find, and you have to find the time taken for the temperature to rise from 8 to 15. I am going to leave this for you to do because that's something that we practiced a lot on. So that's one thing that is a quick work while you are solving before you start solving the assignment. So I want you to pause the video, try solving this on a paper, and then checking your results with the mountain theme that I will post. But I want to solve with you this question. It's about specific latent heat because there is a percentage of efficiency. If we look at this question, we have the mass is 150 grams of an ice block, and its temperature is 0, and it's put in the oven to melt. And they gave us the power of the oven. So we have the power, we have the mass, and we have the efficiency as well. If we want to calculate the time taken to melt the ice, and the specific latent heat of fusion is given, L is given here. The first thing I need to do is, in order to calculate the time, I need to know the power. And I cannot use this power because there's an efficiency. So I need to know how much power is actually absorbed. So I will use the equation of efficiency, which is power output over power input. Because power input is 1,100, but I need to find the power output, which is basically absorbed. So P out multiplication will be equal to efficiency multiplied by power in, which is 0.65 multiplied by 1,100. And if we solve this by the calculator, we're going to get 0.65 multiplied by 1,100, and the answer will be 715 watts. So now we have the power that we are going to use. Now, if I have the power, I can use the equation, which is Q equals ml. To find the time, which is basically what I'm looking for, instead of Q, I replace by power multiplied by time, which is equal to ml. Now, the only thing I have to do is to replace in this formula, and I'm done. So I write 715 times time is equal to m is 0.150. Again, this has to be changed into kilograms. 150 divided by 1,000, which makes it 0.15 kilograms. Multiplied by L is given by 330. One thing here, this L is per grams. So what we have to do is basically keep the mass as in 150. I just paid attention to that. So if the specific capacity is in grams, you keep the mass in grams. So what I am going to do is that I will erase the changes that we did over here because we don't really need that. And here it's just going to be 150. So please pay attention to the units. It's quite important. Good that we got this times 330. So if the unit is in grams, you keep the mass in grams. So as you can see, temperature here will be 150 multiplied by 330 over 715. What you get here is, by the calculator, you get 150 times 330 divided by 715, and the answer will be 69.23 seconds. So if you do this into two significant figures, because we have two significant figures everywhere, that would be just 69 seconds. So that is how you deal with specific latent heat. Again, the reason why I use this equation over here, because they said to melt the ice. I'm not changing the temperature, I'm changing the state. So please pay attention to that. So what I want from you now is to go over this video, try solving the question before that, try solving this question again, and then go over the assignment that I'm going to be posting today. You need to solve it and then submit it before Thursday. All of this is going to be on Digital Campus. We will talk again on Thursday. I'll be opening, by the way, a forum on Digital Campus. If you have questions, you can ask them all there. It gives you the option of sending messages and questions. It's called the forum, and I will be answering them as well. Till Thursday, take care and stay safe. Bye-bye.